Hey guys, this is Stereo Police. That's my username on YouTube, and I'm back with another video, this time on a slightly different topic. Not something I had planned on discussing, but I got a new toy, and you're looking at it right here. It's Keithley 2015 THD multimeter. Keithley is a precision instrument, well crafted, well built. This particular one purchased from a company. It was a company that does calibrations, and they calibrated it, and I have a calibration certificate. Anytime you buy most of my equipment, as you look around the room here, and there's other stuff tucked away, is mostly what I consider to be junk, relatively speaking, including this oscilloscope. Not that Heathkit, that's pretty nice. But this is the best piece, the most precision piece of test gear I have, and it's a voltmeter and many things. It's a signal generator, and too much to even get into it, but it's high precision. I'll give you an example of measuring AC volts. It's going out to 4 decimal places, and believe me, it's accurate. It's not only precise, but it's accurate. Precision and accuracy are two different things. Something could be precise but not accurate, but this is a good piece of equipment, and I mostly purchased it, for my purposes as a hobbyist, tinkering around with audio electronics. I don't need scientific grade precision, but there was one area that I really wanted that precision, and wanted something automated, and that was THD. Total harmonic distortion, and that's what this video is going to be about. By the way, there's a couple. I've seen a couple of videos on YouTube of some guy demoing this thing, and it's all wrong. He got bad results. He used it incorrectly. He didn't set it up right. It's actually kind of simple, but in order to get a precise reading, or to get an accurate reading, it has to be set up right. You have to go through a little setup, and you have to know a little bit about harmonic distortion to know which settings to use and why. He was also using the built-in signal generator, which is not necessary. I am using this BK Precision audio oscillator. And that's another thing I want to talk about, is to get good results, you have to have a good input source. You have to have, the first thing you should do is measure the THD of your input source. If the THD of your input source is something horrendous like 1%, then no matter how good of a piece of an amplifier you have, your reading will always be 1% or higher, because what you're in effect doing is measuring the THD of the input. And these inexpensive signal generators, like that one, and like this little guy right here, I mean, they're okay. They basically synthesize sine waves, but their THDs range from, and I measured them, and they're about anywhere from 0.1 to 0.6% THD, and that's what you're putting into the device that you want to measure. So you're never going to get any better than that. And you might assume you're measuring a high quality amplifier. You might assume, hey, this is a high quality amplifier, but my THD is 0.6, which is not per spec. Well, that's not true, because you're measuring the THD of the input source. This little thing here, which was a $80 audio oscillator, it's a real oscillator. It doesn't synthesize the waveform artificially. It's got built-in oscillators and a high-quality amp, and its THD, I've measured it, at about half its potential amplitude is 0.01 to 0.02%. That's good. That's all I need. So anyway, I'm getting on a tangent right now, because what I want to do, I'm going to do a quick demo of harmonic distortion. Then I want to get into a little bit of theory. And by the way, this video is going to really, the audience of this video is really going to be toward the hobbyist, not the scientist, not the engineer, not necessarily the career technician. Because, you know, when we talk about THD, we could get into the mathematics of it. We could look at Fourier transforms. We could run, you know, we could do some really fun math, but it's not necessary to be a scientist or an engineer to enjoy or even test and measure and repair audio equipment. It's just not necessary. I have a couple of degrees in electrical engineering, and I spent part of my career in electro-optics. And during that time period, I was out of the audio hobby. I didn't want to come home from work every day and do more of this kind of stuff. Now I've been in a different career, more of a legal career now, and intellectual property. And for the last 5 or 6 years, or a little more maybe, I've been getting back into the hobby that I always loved, which is audio equipment. And namely now, I'm more into the classic vintage equipment, both tube and transistor. And it's a lot of fun. And one of the reasons it's fun is it doesn't involve math, to put it bluntly. Not to say that doing math isn't fun, but I'm more hands-on. Yeah, well, I won't get into details, but I no longer like to design amplifiers from scratch and build them. I kind of like to tinker with ones that are, you know, classic equipment, try to figure out what's wrong with them, repair them, test them. That's what I like to do. And one of the many, whether it's a receiver or integrated amp or just flat out power amplifier, stereo or mono blocks, there are several specifications that are important to measure and test to ensure that the thing is doing what it's designed to do and that there's no faults in it. You know, there are things like input impedance, output impedance, and I might make videos about those things. Damping factor, which is directly related to output impedance. That's an interesting topic. Input sensitivity, frequency response, total harmonic distortion, intermodulation distortion, transient intermodulation distortion. The intermodulation and transient intermodulation are things that you typically don't see on a spec sheet. Briefly talk about those. And I'm probably forgetting a few because this is not scripted, it's off the top of my head, but two of the most important things to look at to ensure the amp is of a sufficient quality and functioning properly are frequency response, preferably frequency response at full power, which is called power bandwidth, and total harmonic distortion. Let me write that down. THD. I'll put this on a tripod in a minute. Total harmonic distortion. Okay. There's also intermodulation distortion and transient intermodulation distortion as well, and I'll briefly talk about those. Now, let me say one thing before I do a little demonstration here, then revert back and get into some theory, which to understand the rest of this video or the rest of the series of video, you have to have a fundamental understanding of what THD is, where it comes from, and how it's measured. And then I'm going to get into showing you on the oscilloscope and on the THD meter what waveforms look like versus what their THD is. But one thing I want to say is frequency response and THDs are indicators of whether the amp is working properly, and it's an indicator of the quality of the design, but it's not necessarily an indicator of how the amp is going to sound. Now, certainly when you have horrendously bad frequency response, let's say 100 hertz to 5 kilohertz, you're cutting off quite a few of the frequencies of musical instruments and even the voice to some degree. And or you have horrendously bad harmonic distortion, such as 10%, 20%. I'm going to show you what about 20% looks like in a minute. Certainly you can kind of ascertain from that the amp is going to sound like crap. There's no doubt about it. It's going to. But when you reach reasonable levels, such as 1% THD, and a reasonable frequency response, such as 20 hertz to 15 kilohertz, not many people can hear above 15 kilohertz. And there aren't many instruments that go that high anyway. So if I had an amp that, let's say the frequency response is 25 hertz to 15 kilohertz, and the THD was 2%. That amp, which some tube amps are like that, not this one, but some are, that amp might sound better than a monolithic integrated circuit modern amplifier on a chip, basically, that yields marvelous responses, such as 10 hertz to 200 kilohertz with a THD of 0.0002. That amp might not sound as good. So there's only so much we can glean or learn from frequency response and THD, but certainly it's an important thing to measure. One of the most important things to measure to determine whether your amp is functioning properly, and whether it's a good design. Factors that go into making an amp that yields fairly poor specs sound good. There are many things. There's the quality of the components, there's the nature of the design, there's whether or not it used tubes versus transistors. There's one of the factors that goes into it is there are certain distortions that are pleasing, that sound good. There are certain harmonics that, when added in the right proportions, actually sound pleasing to the human ear. So some distortions actually benefit an amplifier. And then there's the mystery factor that no one really knows. You got people running around putting cones on speakers and I don't know, using fancy, way too expensive cables, and I don't know, just all kinds of rituals and voodoo, basically. There's a mystery factor as well that no one can really explain. The same applies to loudspeakers. So, anyway, before I get into the theory of THD, which is important, let me just give you a quick demo of my setup here. What I've got is I've got a 1 kilohertz sine wave running from an audio oscillator that I know is roughly 0.02 THD, so I'm never going to get better than that. That's feeding both inputs to this gem tube amp that I've elected to keep. I bought years ago, a 300B. And this in turn is driving two dummy loads from both outputs, 8 ohms. I'm only measuring one channel. The red channel that you see on the scope is the input source. That's going to stay constant. I could rotate this little knob and change it, but I've got a good setting there that I need. And the yellow is the output across one of the two 8 ohm dummy loads. And as I rotate the volume knob, okay, you will see the yellow amplitude go higher and lower, and there's the voltage. So I go down to a minimum and have 1 millivolt output, and as I rotate, there's 0.3 volts, 400 millivolts plus, and so forth, and as that goes up, so too will the yellow. Now, we put this camcorder in my left hand here, and I'm going to show you as I get higher and higher in amplitude on the yellow. You can see that let me lower red right there. Okay, you can see that the output, the yellow and the red, you can kind of see how the yellow lags the red in time. That's just the time delay that it takes for the signal to pass through the amplifier and become output. And you can also see that the two sine waves are roughly the same in form and shape, right? And that's a good indicator that there's very little distortion. And let me do a quick setup here. I'll explain to you later on what I'm doing, but to get a good reading here. So I'm measuring THD. It's going to automatically select the fundamental frequency. I want to measure up to 6 harmonics. I can change that, and I want units in percentage THD. There's no filtering done. Okay, now, so right now this amplifier is producing 1.9% THD, and you can't tell the difference really between the input and the output. Can't really tell, right? So as I crank this thing up, I'm going to start here and go to there, and I'm going to show you what happens to the THD. Okay, I'm starting there, and I'm going to go up to where I was before, and now we're at 7.5%, and look what happens. There's a noticeable difference in what those waveforms look like. You can see that the top waveform is starting to get oddly rounded. It's rounding off on the top, and there's the yellow trace is no longer a pure sine wave, and that's because harmonics have been added to it, and those added harmonics are increasing THD. I'm going to go way up. Look at that nasty waveform now, and that is 17% THD. I'm going to turn it down because I don't want to do anything weird to my tube amp. So now tube amps and transistor amps behave differently, okay? And I'm going to get into this too. What you just witnessed there is what's called soft clipping. The peak of that sine wave, you know, here we're at 11%, 12%, 11%. I think I just hit zoom by mistake. My apologies. The peak of that sine wave doesn't just hit a flat top and, you know, a brick wall and just end. It softly clips. Whereas a transistor amp, you'll see hard clipping. Okay, when you reach that point in the transistor amp, okay, that's kind of like soft clipping right there. Okay, that's a tube amp. A transistor amp will go up, hit a rock wall, right? Come down, hit a rock wall, like that. Just boom. And that just all of a sudden adds a ton of harmonics. And you go from 0.1% THD suddenly to 10%, just jumps. Tube amp doesn't do that. It gradually works its way into that that clipping region, and the harmonics increase nice and slowly. Okay, so now I'm going to go to a much lower signal level, and all of a sudden we're at 0.4%. That's reasonable. That's very reasonable for a 300B tube amp. So that's what distortion looks like on the scope versus now. By the way, this is really interesting. Typically, no matter how bad the amp is, you're never going to get more than 50% THD. And again, this is not scripted, I'm just doing this off the top of my head, so I'm probably going to be out of order with many things here, but it came to mind now, so let me just briefly talk about it. So, if you were to, I'm going to say we're going to input a pure sine wave. Okay, one frequency, 1 kilohertz, let's say. Doesn't matter but that's typically what we use. If you were to clip this thing so hard that you turn that sine wave into effectively, there's still a little bit of a slope, but effectively a square wave, that is a little bit less than 50%. Probably like 49, 48% THD. If you were to do something to that square wave, that sine wave, and to turn it into a sawtooth, let's say, I'm trying to, something like that, or something like that, then you'd be looking at roughly 80% THD, and that's pretty damn high, right? Or if you were to turn that sine wave into a triangle, that's not a sawtooth, it's a triangle wave. You'd be looking at something like 13 or so percent THD. So when we're down here and we're for example with the signal I just showed you from the amplifier, when we're slightly rounding off the top like that, what were we measuring? Like 11, 12%? I think we got up to 17% at one time THD. So that gives you an idea about when it comes to percentages. And by the way, my rule of thumb is any amp, good amp, decent amp, any amp should be 1% THD. I should say less than or equal to 1% THD. And at 1%, you still visually can't tell the difference between the input and the output. Let me give you a demonstration of that. Let me crank up the amplitude. 0.99. Okay, there's our 1%. And okay, try to match that. And I'm going to turn the level down a little bit. That's 0.6%. We turn that one up and go up to, that's 1.4%. Okay, I'm just trying to match two. So there's 1.4%, other than the phase shift you see between the two. Match those up a little bit. Look, the right over top, you can't tell the difference. Not a tremendous amount has happened that you can tell, and it's also not that audible, and it just can't be. And what is perhaps audible in the harmonics can actually be pleasing. So when you're around 1%, you can't judge one amp to another. If one amp is 1% THD, probably tubes in that case, and another amp is 0.00003, and it's a heartless, cold, transistorized, monolithic integrated circuit, whatever, that's not going to tell you anything about how these amplifiers compare, in terms of how they sound. On the other hand, if at low signal levels, you're experiencing this ugly waveform here and you're experiencing 70% THD, there's a problem with the amp somewhere. And that's an indicator that something needs to be fixed. Okay, you know, unless you're dealing with a tube amp that's, you know, a first generation tube amp from the 19 whatever, you know, 40s, 30s. I'm not, you know, that it was some amp that shoved into no one gave a shat about, or actually wanted distortion. You know, if it's an amp from the 50s on, let's say, and it was built for audio, it's not going to have 17% THD by design. It just ain't going to happen. So it's an indicator there's a problem. So that's why I measure it. And let me, before I wrap this up, I'm just going to briefly get into the, because I was going to do this in another video, but briefly get into the theory real quick. And for that, let's see, I'm just going to hold the camcorder. So what THD is every audio signal, no matter how complex, is nothing more than the sum of sine waves. The sine wave, the pure sine wave, is the building block for every complex audio signal. And we can sum those sine waves in different ways. Okay, first of all, we can change some things about them. We can change frequency, we can change amplitude and phase. Okay, so we can sum, always we have our lowest frequency, that's called our fundamental. And so we can sum sine waves of different frequencies, sine waves of different amplitudes, and of different phases. And here's what's meant by phase. We can shift where that sine wave starts relative to another sine wave in time. These are three sine waves that are phase shifted. And we bring these all together and we sum them up, and it's going to equal a complex signal. Okay, that's called synthesis. When you synthesize a signal by piecing together different sine waves of different frequencies, phases, and amplitudes. The opposite of synthesis is called analysis. And analysis is where we take a complex waveform and we figure out what it's composed of. We know it's composed of a fundamental frequency and a bunch of harmonics. And those harmonics are integral numbers of the fundamental. You know, so if the fundamental is 1 kilohertz, we're going to have harmonic at 2, at 3, at 4. These are called even harmonics. These are called odd. And these are going to sum up, and these different frequencies are going to sum up with different amplitudes and different phases. And so if we break this complex waveform down into its components, we've done what's called an analysis. And the most common way to do it is a Fourier analysis, which I'm not going to get into. Now, that having been said, distortion is when you add harmonics that did not exist in the original waveform. Now, instead of looking at a complex wave, it's easiest just to look at a sine wave. So, if we have a pure sine wave, and we pass it through an active device such as an amplifier, we get a signal out. What this amplifier will do is two things. It's going to amplify the voltage or the current, whichever kind of amplifier it is, but let's say voltage, and it's going to add harmonics. And that's distortion. No matter how good it is. No matter how good the amp is, it's going to add harmonics. And now, if the amplifier is really good, those harmonics are very low in level, and there are very few of them, and the output wave is going to look just like the input wave, and we're going to have 1% or less, right? Or in the case of that ugly wave I just produced from my tube amp, this amplifier has added many harmonics, probably a first, second, third, and fourth, and those harmonics are going to be much higher in amplitude relative to the fundamental, and they're going to produce this ugly waveform. And that's harmonic distortion. And to measure it, well, I'm going to talk about that later, how these devices work to measure it. But that's what harmonic distortion is. And I'm not going to get into intermodulation or transient intermodulation, but very briefly. Intermodulation distortion is a result of harmonic distortion. So if we look in the frequency domain, okay, this is the time domain right here where we're looking at a waveform. That's time. Okay, let me go back. Okay, that's time, that's amplitude. This is the time domain. We're looking at how a voltage swings in amplitude as time progresses, as time goes on, right? The frequency domain is very similar. We have amplitude, except we're looking at the frequencies in the signal. So if this is 1 kilohertz, in the frequency domain, we're going to have a little line here that represents 1K, and the amplitude of that 1K sine wave. If it's a pure sine wave, this is all we're going to see, a little bar right here at 1K. And it's going to be the amplitude of that, if that's a pure sine wave. But if we add harmonics to it, such as harmonic distortion, and we make it kind of ugly, okay, let's make it kind of ugly, then in order to produce that complex signal, harmonics have been added by the amplifier, and they're going to show up in the frequency domain as other little progressively smaller bars representing the added frequencies. So something at 2K, 3K, 4K, those are even and odd harmonics, and they have their own individual amplitudes. Not so concerned about phase in Fourier analysis with respect to harmonic distortion. It's the relative amplitudes that we're concerned with. Now, with intermodulation distortion, that results from harmonic distortion, and the two track each other. That's just a result of, well, if you're going to add, if you have this fundamental in the frequency domain, and you add another frequency, the first one's going to modulate the second one, just like in amplitude modulation or frequency modulation. And what you're going to end up is you're getting are sums and differences of these two. So you're going to have these other little guys pop up out here in other places. And that's called intermodulation distortion. That can be measured, but you know what? It tracks harmonic distortion. If your harmonic distortion is low, your IM is going to be low too. And not really necessary to measure it. Transient intermodulation distortion, some people used to say this is the most important thing to know about an amplifier with respect to how it differentiates itself in sound quality with respect to a good amplifier. This type of distortion is related to how fast an amplifier can raise the voltage. So let me give you an example. If you have a, I'm going to draw it in the time domain here. If you have a signal, well, let's say you take this audio amplifier and you put a square wave into it. Okay, so here's our input right here. Perfect square wave, right? Perfect rising edges, infinitely rising, flat tops, etc. Well, no amplifier can produce a perfect transient spike. It takes time for that voltage to rise. So what you're going to end up getting is something that looks more like that, and it's kind of exaggerated here. And you have a rise time, and that's the transient right there. And you can see if I put in a perfectly infinitely steep impulse here, and I get this slope output, that's distorted. And that's a type of distortion where you're going to produce some unwanted harmonics, and they're going to modulate themselves, but only during the period of the rise. That's where the word transient comes from. So an amplifier with this is called slew rate, by the way, is this measurement right here. You can look into that. Some amplifiers spec it out, some don't. It's a measure of how well an amplifier can handle transients in the music. And if during those transients it doesn't handle it very well, you're going to get a certain type of distortion that happened during the transients. And that may well reflect itself in terms of how music sounds during transients. I think it's a pretty important measurement. I think that might be, in some sense, more important than THD in terms of how well an amp is going to perform. But I'm not going to get into that. Perhaps I'll make a detailed video about that at a later time. But right now, what I want to do next in part 2 is explain how we measure THD. Explain how this device measures it, and that old device there measures it. And then I want to give you a sample of what THD looks like. Well, we already looked at the tube amplifier, and then I want to put on this little tiny Class D transistor amplifier and show you what it looks like when it clips, and how the nature of the THD. And then also do a demonstration of how THD might change with frequency. I'm measuring it right now at 1 kilohertz, but even at the same input voltage, THD might be different at different frequencies. And by the way, because this is not scripted, I always remember things later, but an amplifier is an active device. Active devices are what produce THD in circuits. Okay, active devices are amplifying devices. Passive devices don't produce THD. Okay, THD is when we are adding harmonics to a fundamental that never existed, that don't exist in the input signal. Passive devices such as resistors don't produce THD. Capacitors and inductors, while they can be used to filter frequencies, what they're doing, if in the frequency domain, let's say I have this nice, this nice signal, whatever my input signal is, and I'm looking at it in the frequency domain. I'm in my workshop, and whenever someone comes rolling down the stairs, it's usually my wife or my nephew who's living here now, and then all of a sudden my video is going to get interrupted, so just turned it off. But anyway, so that's end of part 1, and I'll come back and we'll do some pretty cool measurements and talk more about how these devices work, and about how you can assess how the average hobbyist can assess THD with some pretty basic equipment. Kind of already talked about that a little bit, but all the way up to the use of one of these, the Keithley here, which I highly recommend if you want an accurate indication of THD. This does it for you. This is a precision instrument. It's wonderful. It's fantastic. By the way, these are typically $5,000 or more. Keep an eye on eBay. Buy from a reputable user, preferably a company that calibrates. And you can get these for around $500 or less, a little more maybe. It's a precision voltmeter. It's my best voltmeter. It's a precision signal generator. It's many things that I'm not even getting into. This thing is fantastic. And another thing you'll need is a high quality signal generator, but not just a signal generator, not just a function generator, but an audio oscillator. There's this one. BK makes another one that I purchased recently that's on the way. It's a larger one with a big dial on it. And a low distortion audio oscillator, something that's around 0.001 THD, something like that. That's a must. Otherwise, you're just measuring the distortion of the signal source. So, we'll get into more about that later. Thanks for watching. I hope this was helpful. If it was helpful, send me a comment. I never ask for thumbs up, but it's always nice. And hey, I'll see you for part 2 of this in just a bit. Ciao.